Hello and a very warm welcome to each and every one of you watching. Before we dive into today's incredible topic, I want to take a moment to say how truly grateful I am that you're here, spending your valuable time with me. In a world that can sometimes feel so busy and chaotic, it means the world to me that you've chosen to click on this video. I genuinely hope you and your loved ones are feeling happy, healthy, and strong today. Wherever you are in the world, I'm sending you my very best wishes and positive energy. Let's jump in. Today, we're going to talk about one of the most powerful and awe-inspiring forces of nature, the tsunami. But we're not just going to talk about the giant, devastating waves that crash onto the shore. We're going to go on a journey, a deep ocean journey, to understand how a tsunami can begin in one part of the world and travel, with relentless energy, across entire oceans to crash onto a shore thousands of miles away. It's a story of unimaginable power, hidden in plain sight beneath the waves, and it's a testament to the interconnectedness of our entire planet. To really get our heads around this, we have to start at the very beginning, with what causes a tsunami in the first place. Most of the time, the ocean is calm on the surface, but the earth beneath it is incredibly active. Think of the Earth's crust not as one solid, unbroken shell, but more like a gigantic jigsaw puzzle made of enormous pieces called tectonic plates. These plates are constantly, slowly moving, sliding past each other, pushing against each other, or even diving underneath one another. Now, imagine two of these massive plates getting stuck. They push and grind against each other, building up immense pressure over years, decades, even centuries. It's like you're pushing your palms together as hard as you can. Eventually, the stress is too much, and one plate suddenly lurches upward, catapulting over the other. This sudden, violent movement on the ocean floor is what we call an earthquake. But this isn't just any earthquake. It's a specific kind that lifts a colossal section of the seabed, sometimes for hundreds of miles, in a matter of seconds. This monumental lift doesn't just move the rock, it moves all the water that was sitting above that rock. In an instant, trillions of gallons of seawater are displaced. You've essentially punched the ocean from below. This is the moment a tsunami is born. It's not the only way. A massive landslide into the ocean, a volcanic collapse, or even a volcanic eruption can do something similar, but this tectonic earthquake is the most common creator of these ocean-spanning monsters. Now, here is the first big misconception people often have. When they picture a tsunami wave out in the deep ocean, they imagine a towering, 100-foot wall of water, like you see in the movies, racing across the sea. That is not what it looks like at all. In the deep, open ocean, a tsunami wave is actually incredibly subtle. It's a wave, yes, but it's a wave of energy, more than it is a wave of water. Because the source of the wave is so vast, the entire section of lifted seabed, the wave itself has a wavelength that is unimaginably long. Wavelength is just the distance from the crest of one wave to the crest of the next. For a normal wind wave you see at the beach, the wavelength might be a few hundred feet. For a tsunami, the wavelength can be 100 miles long or even more. Because it's so long, and because the ocean is so deep, the wave energy is spread out over a huge volume of water. This means that out in the deep ocean, the wave might only be a foot or two high. A ship sailing over it would probably not even notice. The people on the ship would feel a gentle, slow rise that lasts for several minutes, as if they were going over a very, very wide and soft hill, followed by an equally gentle and slow descent into a trough. It would be so gradual that their instruments might detect it, but they would likely feel nothing unusual. This is the secret of the tsunami's long-distance travel. It loses very little energy as it moves because it's not fighting much drag or friction. It's moving through the entire deep layer of the ocean. And move it does. Once that energy is injected into the ocean, it radiates outward from the source, the epicenter of the earthquake, in all directions. It doesn't go in one direction, it forms a series of expanding rings, much like the ripples you see when you throw a pebble into a pond, but on a planetary scale. The speed of these waves is where things get truly mind-boggling. The speed of a wave in the ocean is determined by the depth of the water. The deeper the water, the faster the wave can travel. In the deep, open Pacific Ocean, which has an average depth of around 13,000 feet, a tsunami can travel at speeds rivaling a jet airliner, reaching an astonishing 500 miles per hour. Just stop and think about that for a second. A wave, a pulse of energy, is moving through the ocean at the speed of a passenger jet. It can cross the entire breadth of the Pacific Ocean, a distance of over 10,000 miles, in less than a day. This is how an earthquake off the coast of Chile can send a wave that, hours later, arrives in Japan. The ocean, in this context, acts like a superhighway for energy, transmitting this powerful signal from one continent to another with terrifying efficiency. This journey across the ocean isn't just a straight shot, the wave interacts with the underwater landscape, the topography of the seafloor, in fascinating ways. Features like mid-ocean ridges, which are massive mountain ranges under the sea, and underwater valleys can focus the wave's energy in some directions and scatter it in others. It can bend, a process called refraction, as different parts of the wave front travel at slightly different speeds due to variations in depth. Scientists can actually map the pathways of this energy across the ocean. It's not a simple ring, it's a complex pattern shaped by the hidden geography of the deep sea. Furthermore, as this wave train travels, it's not just one wave. That initial shove of the seabed creates a series of waves, a wave train, that radiate out. So, the first wave to arrive on a distant shore is not necessarily the biggest. There can be several waves, sometimes separated by tens of minutes to over an hour, and the third or fourth wave might be the most powerful. This is why authorities always warn people to stay away from the shore for many hours after the first wave has hit. The danger is not over. So, we have this incredibly fast, incredibly long, but very low energy wave cruising through the deep ocean. How does it transform from this gentle, almost imperceptible swell into the devastating wall of water that we know and fear? The answer lies in what happens as it approaches land. This transformation is all about the relationship between the wave and the seafloor. Remember that incredibly long wavelength? As the wave moves into shallower water, something profound happens. The bottom of the wave, which was moving freely in deep water, begins to feel the drag of the seabed. It starts to slow down. However, the top of the wave, the part near the surface, is still trying to move at its original, faster speed. This creates a pile-up effect. The wave's energy, which was spread out over 1,000 feet of water depth, is now being compressed into a much shallower column. The only direction for this energy to go is up. The wave slows down dramatically, from hundreds of miles per hour to maybe 20 or 30 miles per hour, but it grows tremendously in height. The water literally builds up, creating that characteristic towering wave. This process is called shoaling. But the shape of the coastline and the underwater slope leading to it play a huge role in determining what kind of wave arrives. A very steep underwater slope might cause a powerful but shorter surge. A long, gradually sloping continental shelf, or a V-shaped bay or river estuary, can focus the wave's energy like a funnel, amplifying its height to extreme levels. This is why some areas are far more vulnerable than others. The wave is also behaving differently now. In deep water, it was a wave in the ocean. In shallow water, it becomes a moving wall of the ocean. It's not just water on the surface moving, the entire water column, from the surface to the seabed, is in motion. This is why a tsunami doesn't arrive like a normal wave that breaks and recedes. It arrives as a fast-moving, powerful, and terrifyingly deep torrent. It can look like a rapidly rising tide, a series of breaking waves, or even a bore, a vertical wall of churning water. It doesn't crash and retreat, it keeps coming, flooding miles inland with unstoppable force, carrying immense amounts of debris and causing unimaginable destruction. The aftermath is just as complex as the wave itself. After the initial surge floods inland, the water doesn't just sit there. It has to go back out. The retreat of the water is often just as powerful and destructive as the incoming wave. It pulls everything, cars, trees, pieces of buildings, and sadly, people, back out to sea. And this cycle can repeat with each subsequent wave in the train. The force of the water is so immense that it can scour the land down to the bedrock, eroding beaches and foundations, and depositing sand and ocean sediment far inland. The saltwater inundation poisons farmland and freshwater supplies for years to come. The human tragedy is, of course, the most devastating aspect, which is why understanding the science is so critical for early warning and survival. This brings us to the crucial question: how do we know a tsunami is coming across the ocean, and how do we warn people? This is a monumental task of international cooperation and sophisticated technology. It starts with seismic monitoring. When a major earthquake occurs anywhere in the world, seismic centers around the globe detect it almost instantly. Scientists can quickly analyze the data to determine the location, depth, and most importantly, the type of earthquake. If it's determined to be the kind that can displace the seafloor, a shallow, strong quake under the ocean, a tsunami watch is immediately issued for the surrounding region. But to confirm that a wave has actually been generated and to track it across the ocean, we need eyes in the sea. This is where an amazing technology called a DART buoy comes in. DART stands for Deep Ocean Assessment and Reporting of Tsunamis. These are specialized buoys anchored to the seafloor in the deep ocean. They have two parts: a pressure sensor on the seafloor that measures the weight of the water above it with extreme precision, and a surface buoy that communicates the data to a satellite. Normally, the pressure is constant, but when a tsunami wave, with its massive volume of moving water, passes over the sensor, it detects the slight increase in pressure. Remember, that wave in deep ocean is only a foot or two high, but it's a foot of water moving over a huge area, so the pressure change is detectable. This data is relayed in real time to tsunami warning centers, like the Pacific Tsunami Warning Center in Hawaii or the National Tsunami Warning Center in Alaska. These centers run complex computer models that take the earthquake data and the real-time wave data from the DART buoys to predict the tsunami's behavior, its speed, its direction, and most critically, its expected height when it reaches coastlines around the ocean basin. They can then issue precise warnings, telling authorities in distant countries exactly when to expect the wave and how big it might be, giving them precious hours to evacuate coastal areas. This system is not perfect, and it requires constant maintenance and public education to be effective. The story of the 2004 Indian Ocean tsunami is a tragic example of what happens without such a system. A massive earthquake off the coast of Sumatra generated a tsunami that radiated across the entire Indian Ocean. Without a warning system in place and without public knowledge of the natural signs, like the sea dramatically receding, hundreds of thousands of people were tragically caught by surprise in dozens of countries. That event was a somber wake-up call for the world, leading to a massive international effort to establish warning systems in all the world's oceans. The raw power of a tsunami to travel across an entire ocean is a humbling reminder of the forces that shape our planet. It connects us all. An event in one hemisphere ripples out and touches the lives of people in another. It shows that the ocean is not a barrier separating continents, but a dynamic, fluid body that links them together in the most dramatic ways possible. Understanding this phenomenon is not just about satisfying scientific curiosity, it's about saving lives. It's about respecting the power of nature, being prepared, and working together as a global community to mitigate the risks. The next time you see the ocean, calm and peaceful, remember the incredible, hidden energy that can sometimes pulse through its depths, connecting faraway shores with a message written in water, a message we must learn to read. Thank you for joining me on this journey across the deep ocean.